In this lesson, we're going to teach you how to manipulate expressions that involve surds. I want to start by reminding you that surds are defined by the following expression. We say that the bth root of a is the same thing as a to the power of 1 on b. I explained this in much more detail in the introduction to surds, but for now we're going to see how we can use this to simplify a bunch of expressions. So if we use this expression and the index laws, we can write a whole bunch of different relations between expressions that involve surds. For example, if we start with the bth root of a all to the power of c, we can rewrite this using this formula. Now after this, we can go ahead and multiply this 1 on b by this c, which will give us c on b. Now at this point, I could say that this left-hand side equals the right-hand side, and I could call it a day. But instead, I'm going to move this 1 on b to the outside, because I want to show you a rule that's a little bit more useful. We can see that a to the power of c, all to the power of 1 on b, is going to be the exact same thing as the bth root of a to the power of c. And this is actually the first of our useful rules. I want you to see that if we have a power outside of the surd, we can bring it inside of the surd. And if we have a power inside of a surd, we can also take it outside of the surd. Both of these sides are exactly the same. Now, I don't think a rule like this is very useful if you don't see how to use it. So how about I give you an example to show you why this rule is actually useful. So suppose we wanted to evaluate the cubed root of 4 all to the power of 2. Well, the first thing we should do is we should bring this 2 inside of the cubed root. So let's do that first. Now we can replace 4 squared for the number 16. So for now, I'm going to leave this as the cubed root of 16. But as you're going to see in a couple of minutes, this can be simplified even further. Now for the next expression, I want you to consider what would happen if we had the bth root of a to the power of b. So instead of c here, we actually make this equal to this. Well, let's start by writing the root in index form again, and we'll try to simplify it. Now at this point, we can say that the bth root of a to the power of b is the same thing as a to the power of b all to the power of 1 on b. But then using the index laws, we can say that b times 1 on b is the same thing as 1. But of course, you don't really need to write the power of 1, so we could just write this as a. This rule says that the bth root of a to the power of b is the exact same thing as a. So that means whenever you have this form, you can cross out the b's. We can explain this rule by saying that equal powers and roots cancel each other out. So the bth root cancels out the power of b, and you're only left with what's inside. But I should give you an example of this as well. So if we wanted to evaluate the square root of 5 all to the power of 2, then one thing you need to remember is that the square root of 2 implicitly assumes that there is a 2 over here. We just don't write it because it would be annoying. And now, remembering the first rule, we can bring this 2 inside the square root. And now, because we can cross the b with this b, then we can cross this 2 with this 2, and the answer is just 5. Now this immediately tells us that the square root of 5 all squared is exactly the same thing as the square root of 5 squared, and both of those are the same as the number 5. And now this brings me to one final rule. This time, I want to look at the cth root of a times b. Note that there's a multiplication inside the root. Well, as usual, I'm going to go ahead and write this without the surd, so I'm going to write it in this index form. Now, using another index law, we know that we can distribute 1 on c to both the a and the b. So let's do that as well. But now, at this point, I want you to see that a to the power of 1 on c is the same thing as the cth root of a, and b to the power of 1 on c is the same thing as the cth root of b. So we can go ahead and replace them for their root forms again. So we can see that the cth root of the product a times b is the same thing as the cth root of a times the cth root of b. and therefore we can say that a product of roots is the same thing as a root of products. So let me demonstrate this with an example as well. So we want to evaluate the square root of 3 times the square root of 2. This time I'm not going to write the implied 2, but I want you to remember that it's there. But either way, our rule tells us that we can just multiply 3 times 2, and we can write this as a single root. And of course, we can replace 3 times 2 for 6. So therefore, the square root of 3 times the square root of 2 is the exact same thing as the square root of 6. Earlier, I mentioned that you could go a little bit further with the first problem that I actually gave you. So to show you this, I'm going to go ahead and continue it right at the bottom. If we wanted to simplify this even further, one thing we could do is we could write 16 in terms of its prime factorization. 16 is the same thing as 2 to the power of 4, so I'm going to replace 16 for 2 to the power of 4. But rather than just leave it as 2 to the power of 4, we notice that it's inside of a cubed root. So that means it's a good idea to break it up into a 2 cubed and a 2. But then at this point, we might as well use this rule over here to break this into 2 different roots. So you'll get the cubed root of 2 and the cubed root of 2 cubed. But as we know, we can rewrite the cubed root of 2 cubed as 2, because the power just ends up crossing out with the root. And finally, that tells us that the cubed root of 16 is the same thing as 2 times the cubed root of 2. So to simplify anything like this, you first start by rewriting it in terms of powers of the outside, and then you try using the multiplication rule and you try crossing things out to get things like this. Now at this point I want you to realize that the surds are really just like normal numbers. They have their own rules that they follow, and they have their own arithmetic, but they have a key difference to normal numbers. A number like the cube root of 16 can be rewritten as 2 times the cube root of 2. Now, the number 2 can easily be computed, but then the cube root of 2 is much more complicated. Remember that we can always approximate the cube root of 2 as closely as we like, but we can never really write down the full cube root of 2 because it would take an infinite number of digits to do that. Despite this, however, if we did actually figure out all the decimals of this number and all of the decimals of this number, we would actually end up with the exact same number. No matter how long we compute this or how long we compute this, we'll always end up with all the same digits. Now, if surds really are just normal numbers, then all of the rules we've learnt so far should just apply to them without any modifications. So, for example, if I asked you to expand the square root of a plus the square root of b, all squared, then we can go ahead and use the normal rule for a binomial expansion. We start by squaring the square root of a, then we square the square root of b, and then we multiply by 2 times the square root of a times the square root of b. Now after this, I want you to remember that the square root of a has an implied 2 over here, and therefore we can go ahead and cross this root with this power of 2. And then we can do the exact same thing for the next root. Now after this, we can use the fact that a product of roots is the exact same thing as the root of a product. So the square root of a times the square root of b is the same thing as the square root of a times b. So therefore we can see that the square root of a plus the square root of b all squared is the exact same thing as a plus b plus 2 times the square root of ab. So at this point, I'd just like to summarize this lesson. We just saw that the bth root of a is the same thing as a to the power of 1 on b, and using that we were able to come up with a bunch of expressions that help us simplify surds. We saw that you can move powers inside or outside of roots. We also saw that equal powers cancel roots, and we saw that you can write a product of roots as a root of products. I showed some examples of how to use all of these, and I also showed that the rules of algebra that we've learned so far apply directly to surds without any modifications. Now that you understand the arithmetic of surds, you're very likely going to see them used much more frequently. Anytime you have any doubts about any of the rules of surds, you can always rewrite them as an index, and then simplifying your expression should be a fair bit easier. But I think that just about completes our discussion on the arithmetic of surds. Thanks for watching another Trina video. If you want to say thanks, you got to show your friends. Or maybe you should just visit us at trina.org, where you can track your progress and have access to questions and heaps of other awesome stuff. Or maybe you should just like and subscribe. That works too. But either way, I'll see you next time.